Hello, welcome back. Today we have lecture 49 and today is the last lecture for our discussion on bipolar RF devices. We were talking about silicon germanium HBT, the basic layout and structure, and today we are going to discuss and conclude that, and we will also conclude with a short note on the differences between bipolar devices and FETs for RF applications. Okay, so over to the whiteboard here. So, in silicon germanium HBT, the fundamental question is, why do people introduce germanium in the base to make it silicon germanium? You know, the base is silicon germanium. So, what is the reason for having germanium in the base? The reason is because you can tune the band gap, and it helps increase or improve certain device property. So, what is that? So, you just do not normally introduce germanium, you grade the germanium. The composition of germanium keeps changing. Typically what you do is that the top picture here, this picture, on the y axis you have germanium concentration, okay. On the x axis you have the thickness or the depth. So, you can see this is the base, you know, from 0 to WB, this is your base, and you can see that over the base the germanium concentration is increasing from the emitter side to the collector side. Okay. So, the germanium concentration is, this is a silicon emitter and there is a silicon collector, but the base is silicon germanium and the germanium concentration is gradually or most likely linearly increased from the emitter side to the collector side. So, as you increase the germanium concentration, the band gap becomes lower. So, from the emitter side to the collector side, the band gap becomes lower. Okay. So, the electron the conduction band profile looks something like that. So, this is the silicon conduction band profile of the emitter, this is the silicon collector. In the base what you have is that germanium concentration will start from some x percentage and it will go to some y percentage where y is greater than x. So, the discontinuity on the emitter base side is low because the germanium concentration is low. So, the band gap of silicon germanium here is kind of almost equal to that of silicon with small difference. However, at this side the germanium concentration is higher, which means the band gap of the alloy is also much lower. So, the discontinuity, the conduction band discontinuity between the germanium silicon base and the collector, the silicon collector, is pretty large, that is why you see that. So, this is your total difference in the band gap that has arisen because of the grading. Okay. This is the discontinuity between the band gap and the emitter side, between the silicon emitter and the silicon germanium base, and this is not the total discontinuity. Okay. Look at the dotted line here, is the total difference in the band gap that has arisen because of the grading of the base. Now, this grading of the base makes, you know, a slope in the conduction band something like that. So, your electrons can actually travel faster because there is an additional electric field, we call it the quasi electric field or quasi electric field. If you remember, we talked about it. This electric field arises not because of an external voltage or internal bias that you are applying, it is because of the grading of the composition that sets this field up, and that will tend to accelerate the carriers. So, you will reduce the transit time and increase the cutoff frequency, that is point number 1. Point number 2 is that germanium in the base also increases the beta, because of course you have the band discontinuity. So, your beta, the back injection and other things you can tailor such that your overall gain increases. Okay. And because of a lower band gap material in the base, your base resistance also drops, because now you can actually increase the base doping a lot without having to worry about the emitter doping, because it's the same principle as a L-gas HBT. You have a wider emitter and you have a narrower base. Okay. So, of course the base can be doped much higher now, because you do not necessarily need the emitter doping to be higher than the base doping in order to have a finite gain. Because of this discontinuity in the conduction valence band, you actually are going to get a much higher gain anyway. So, silicon germanium in the base helps improve the base resistance, has the grading in the base helps improve the transit time, improves the beta. Okay. And all these things will help improve the noise figure, for instance, because if your base resistance comes down, and why is the base resistance coming down? Because you are doping the base high, which you cannot do so much in silicon BJT. So, because of that base resistance comes down. If the base resistance comes down, remember the gate resistance, your cutoff frequency will improve, your noise figure will reduce, both are very very good and helpful. Okay. That is what I said. And there is also an impact on the early voltage, okay, because you are grading the base. So, you can dope it high, and the depletion from the base collector towards the base can be prevented, and that gives rise to a very large early voltage, which is helpful. Okay. Now there are different layouts of silicon germanium HBT. Just this is a schematic to show that there are different layouts. For instance, here you have one emitter, one base, one collector. Here you have one emitter, base both sides, collector only one side. In other case, you have emitter 1, you have both base on both sides and then collector on both sides also. These different layouts are used by designers to their advantage. You can use these different designs to improve certain parameter to design the layout of the circuit that you have. So you can choose from different designs, but again there are trade-offs to pay with certain with scaled up devices, scaled down devices. You cannot always go for one layout or one other. There will always be trade-offs to play. The bottom 3 panels here show essentially the top view. The top panel here is the cross section. The bottom panel here is the top view. You can see this is the emitter line, the emitter contact. This is your collector contact, and then the base is like a ring here, but because the base is only one side, that's why you have this. These are the via holes through which you will put the tungsten maybe, and then you will make a via hole to connect the base upwards as you integrate them. So this is only one side you have base, but if you have a base like this, both side, then you have via holes here also and here also, and this via holes on the side are basically your substrate connection. Similarly, you have 2 collectors here. This is one collector, this is one collector. Base is again via hole. The base has via holes, but the emitter doesn't have via hole, at least in this layer here, in this level here, and the collector doesn't have, because the emitter and the collectors are like a continuous metal bar, because the emitter and collector will carry high current. That's why the base does not carry high current. You have these via holes to carry it upward. Okay, and each via hole can introduce some resistance, by the way, but that's something we need to remember in designing HBT. Okay. Now these are some of the points that I am mentioning. It's very important to note down and just understand. There's nothing to understand much, but it's just important facts that you have to remember is that the number of this, we call this actually the fingers as stripes. The number of stripes that you have in emitter, base, collector, both sides, single side, etc. will definitely impact your high frequency performance, because for instance you have collector on both sides. This is the first collector, this is the second collector, which means your collector is now coupling to the substrate on both sides. So the collector substrate capacitance is double. Your base collector capacitance also has increased because you have collector on both sides. Here there's collector only on one side. So then your capacitances is lower. So this should give you better high frequency performance than this. However, if you have 2 collectors on both sides, then your collector resistances can come down because you're feeding electrons from the both side, or you're taking electrons out from both sides, and so your collector resistance can drop. But there's a trade-off now, whether you want to actually reduce the collector resistance or whether you want to reduce the collector capacitance, because both of them will trade off with each other. So again, it depends on the design that you have, on the technology node that you have. For very highly scaled device, maybe the capacitance is a more killing effect than the resistance. Okay, so those things are very pertinent in this discussion. So the circuit design, okay, so that's why you have an impact on high frequency noise performance, we know that. The circuit designer, they generally play with the emitter length. I told you, and emitter width is typically not a given parameter to play with. The emitter length in modern silicon germanium BiCMOS process could be 0.5 to 15 micron. It's a few years old, of course, so it could be even less than 0.5 micron now. Now typically 2 to 3 emitter stripes are used. This is silicon germanium HBT. This is not compound semiconductor HBT. In compound semiconductor HBT, you have multiple fingers, you carry higher currents, but in silicon germanium you typically carry lower currents, absolute currents, and then you have only 2 to maximum 3 emitter stripes. Otherwise electromigration, current crowding and other effects will become more severe, and so you have to basically parallel connection 2 or more HBTs, silicon germanium HBTs, if you need more stripes here. Okay. Now let's look at the dimensions. This is your emitter finger width, of course. This WSP here refers to the spacing between the emitter foot here and the base polysilicon external start over, the layer over there. So this is basically the you can say this part is basically the spacing between the emitter foot and the start of the polysilicon p-type base, and this is an oxide spacer. You see, oxide or nitride spacer is there, right? So that you keep it in mind. This is actually your selectively implanted like a pedestal collector, but then it also laterally diffuses out. So this part is a part of your collector very much. This is a part of a collector very much, but this is called the extended part of the SiC, the selectively implanted collector. This is your sinker width, and of course there will be a sinker length also, that in the dimension. This is the sinker junction depth x, and this is the lateral distance between the center of the collector to the center of the emitter. Okay, this is your spacing between, this is the lightly doped collector, the spacing between the selectively implanted collector including the diffusion extension to the shallow trans isolation. Okay. Same things are also shown here. This is the length of the sinker, okay, and this is the length of the emitter, this is the width of the emitter, this is the WEC, the center of the collector to the center of the emitter, and so on and so forth. Okay. So these are the dimensions just to keep in mind, because we are going to discuss about the parasitic resistances now. That is why it is just generally helpful to just remember these different dimensions here. Okay. So now if I this is basically a silicon germanium parasitic resistance profile. This is a compound semiconductor parasitic resistance profile. You can see that a compound semiconductor relatively looks much simpler here, because the compound semiconductor just has an emitter resistance, a base external resistance, a base internal resistance, and then a collector resistance here. That is all. Okay. That is what this schematic also shows. But in a silicon germanium process, it is fairly complicated. As I told you, silicon germanium is actually grown. You have p-type silicon from the side. Okay. Actually this is called like a double, this typical silicon germanium that you are looking at typically, it is called double polysilicon, because you have polysilicon this side, you have polysilicon this side on which you contact the base, and this polysilicon contacts the intrinsic silicon germanium base here, right. So this is called double polysilicon self aligned. This is a self aligned process again. The spacer thickness you see here, very much like the compound semiconductor thing, the spacer thickness will determine the spacing between the emitter edge here and the base edge here. Okay. So it is a self aligned process. So double polysilicon self aligned, so DPSA, double polysilicon self aligned, and this is HBT, silicon germanium HBT. This could be epitaxially grown or non epitaxially grown. There are many different types, but this is a double polysilicon self aligned epitaxially grown, maybe a silicon germanium BJT process. Is fairly complicated, the entire fabrication steps here. But anyways, for this particular discussion, what we need to remember here is that there are different resistances here. Of course, there is an emitter resistance, the intrinsic emitter polysilicon resistance, the emitter metal to the polysilicon contact resistance. There is this intrinsic base resistance inside the silicon germanium base, then there is this extrinsic resistance in the polysilicon. There is also a resistance here that is below the oxide spacer, that is an extrinsic resistance, but it is below the oxide spacer. There is the sinker resistance here, which should be low, of course. Then there is this lateral collector subcollector spreading resistance here, right. The substrate resistances are of course there, which we are not talking about that, but we should. Then these are the RCon actually stands for this via hole resistance, like you have these holes and then you are taking them out contact, it is a contact from layer to layer. So they can add 10 to 15 ohm per contact. Actually tungsten contact resistance is fairly large in a 130 nanometer BiCMOS process. Okay. This is the tungsten squares to contact the external base poly to substrate, so many things are there. Again, this is the side view and this is the top view. So you can see that there is this emitter resistance here, there is this base intrinsic resistance, the base extrinsic resistance, the sinker resistance, substrate resistance, and so forth and so forth. So if I look at the emitter resistance, the thing is that the emitter resistance is very critical, because it will affect, it will dictate or it will influence the base emitter forward bias at which you are going to observe the device performance. You are applying certain forward bias to the base emitter. If your emitter resistance is terrible, then a lot of voltage is going to drop on that, as high as 50 millivolt can drop on that. And remember, these devices operate at very low voltages, so 50 millivolt can be significant. So if you drop such an amount of voltage on the excess parasitic emitter resistance in general, including parasitic intrinsic plus extrinsic, then what you are going to see actually in the base emitter junction is lower. So you need to apply even higher VBE to observe a peak performance. So the emitter resistance can affect the DC behavior very much. It will dictate or it will decide at what base emitter applied voltage you are going to see the peak performance. It's like the source resistance in an FET. Okay, so source resistance affects the GM, the gain, remember. Similarly, your GM in a BJT or an HBT here also will be affected by the emitter resistance. So you want the emitter resistance to be low, otherwise your gain will reduce, and that reduces, the reduction in gain also will reduce the cutoff frequency. And if the cutoff frequency reduces, your Fmax also will reduce, because that depends on FT, and if your Fmax reduces, your noise figure will also become worse. So everything is dependent on the emitter resistance. You really want to lower the emitter resistance, it is just like the source resistance. Okay. So you can see the emitter resistance is pretty much the contact between the metal and the emitter polysilicon, and the polysilicon emitter itself, the resistance of the polysilicon emitter itself. Now RSE here is actually the sheet resistance of that, or you can say the unit resistance, normalized unit resistance ohm centimeter square for the emitter polysilicon, including the contact resistance, and the total absolute ohm you have to multiply by the area of the emitter stripe, which is the length times the width. So as in a highly scaled device like 130 nanometer, 90 nanometer, 65 nanometer, etc., your length and width both needs to be scaled down or reduced, and then it leads to an increase in the emitter contact resistance or overall emitter resistance. That's not good. So with decreasing or with aggressively scaled nodes, the emitter resistance becomes a more concerning factor. Okay. Next is the collector resistance. Now if I have a single collector, a collector that is only collecting from one side, not both sides, you can see there is a single base, there is a single collector. It is fairly simple. You have a sinker resistance here, and that sinker resistance is this, and then you have the base collector, the below the actual this part, you have this spreading resistance here, right, which is this. Very easy. This first part is basically you take the sheet resistance of this part here, okay, which depends on the doping of the layer, the thickness, etc., and then you multiply by W by L. Very simple. Similarly, the sinker resistance is like a 3D block going vertically down. That is why you have the sheet resistance of the sinker layer, which again depends on the doping there, but here you have a square of the junction depth. This junction depth is x, s and k, square of the junction depth divided by the area. Okay. So why the square and this area comes here is because you have like a vertical 3D block going down. That is why this area comes into picture. Okay. Now if you feed this from both sides, imagine there is a collector on the other side also, like the image here. Yeah, there is a collector on the first side, collector on the both side. So both collectors will be feeding or electrons here or taking the electrons out here. In that case you have to divide this by half. So there is a factor of 2 here, there is a factor of 2 here, that is all. This is your collector, total collector resistance in the silicon germanium HBT. Okay. Remember, the collector resistance depends on the doping of the collector, this region, it also depends on the geometry such as the thickness and what kind of layout you are putting, okay, buried layers. It affects your VCE. Think of this as the drain resistance in FET. If you have a higher drain resistance, you are going to block more voltage, but your on resistance will suffer, and you have to apply higher drain voltage to observe the desired peak performance. So similarly, the collector emitter voltage at which you are going to see the desired performance will be pushed out. So you have to apply higher voltages because you are going to drop unnecessary voltages in these resistances. Okay. Sometimes people use 2 collector stripes like that because you want to lower the collector resistance. If you are feeding electrons from both sides, taking electrons out from both sides, then you tend to reduce the collector resistance. However, if you go to very scale device geometry like 0.13 micron or less than that, something like that, then this does not hold true anymore because each of this is coupling capacitively to the substrate here, correct. So that the collector to substrate coupling capacitance becomes twice with 2 pads, and that will kill the overall device. So the improvement you get with reduced collector resistance is more than offset by the increased or worsening collector to substrate coupling capacitance in a highly scale like submicron HBT. So this only applies, these 2 types applies only to like larger kind of HBT, traditional HBTs. Okay. Then comes the base resistance, and base resistance is very critical. We know the base is the most important layer here, it's so critical. So of course you have an intrinsic base here that depends on the base width, the neutral base width, and the base doping, correct. The thickness of the silicon germanium base that you are putting, the base doping you are putting. Why emitter width? Because the top width here also defines the the base. Base is actually intrinsically below the emitter, so that is why it defines that. So base doping, base thickness, emitter width, they all determine your base intrinsic resistance. There are extrinsic resistances. There are I think 3 components of extrinsic base resistance. So there is a silicon germanium base region below the spacer. You see, this is the spacer. So below the spacer there is a resistance which is just outside the intrinsic. So the intrinsic is this part. So just outside the intrinsic there is this resistance below the spacer. Then there is this unsolicited, because whenever you put a silicide layer you kind of tend to lower the resistance, but there is an unsolicited external base polysilicon region below the emitter oxide which should be here, which should be here, the edge of that, it's not salicided. Okay. And then of course this polysilicon resistance also will matter here, correct. And then you have a salicided external base poly. If you have a salicided layer here, then that particular resistance will come in the 3rd component here. Okay. And of course this contact resistance of the base metal to the base polysilicon layer, all of this combined to give you the base external base resistance, and then there is an internal base resistance. Okay. So the base doping and the base width, typically intrinsically speaking, they are lumped together and called base sheet resistance, and this is something you can measure experimentally from test structures. Okay. It's like the intrinsic device, you can think of that. Okay. So that is about the base resistance, but it is very important just to keep in mind. Okay. The next comes the capacitances, and you can see that in silicon germanium capacitance, the structure here, there are enormous number of capacitances. Okay. That is because of the more complicated DPSA process that I told you, double polysilicon self aligned process. Because of that, the way the layout is, even cross section wise, it gives rise to an enormous number of capacitances. So you can see that there is this extra capacitances coupling between the emitter polysilicon to the base polysilicon through the oxide, the spacer oxide. These are extra capacitances that are coming in picture. This is the base emitter capacitance, this is the base collector capacitance, this overhangs here, they can give rise to extra coupling capacitances here. Through the deep trench isolation, there can be coupling capacitances. Through the shallow trench isolation, there can be coupling capacitances. Okay. But in general, the forward bias base emitter junction gives rise to diffusion capacitance. We have talked about it enormous time. There is also a junction capacitance which you can tend to ignore, but this will typically depend on the periphery. And then there is an oxide capacitance which I already talked about, and this depends on the periphery, because this is on the side. No, so if you look from the top, this is essentially the periphery of the emitter coupling to the base polysilicon layer here. So this is basically proportional to the emitter periphery. Okay, and this has to be included in the emitter capacitances because of this overhang of the oxides there. So the intrinsic base collector capacitance, this is the intrinsic capacitance per unit area, and then you have to multiply by the length of the finger into this. What is WE plus 2BCE? See, the base collector capacitance, there is an intrinsic base collector capacitance per unit area, correct? You have to multiply it by the area. What is the area? One of them is LE, because that is your finger. If I look from the top, this is your active device or intrinsic device. This dimension is your dimension is your LE, that is your intrinsic device length, the emitter length, you can say, that has to be there. And why is this WE is this? Why is the 2BC? 2BC is basically the laterally diffused selectively ion implanted, I will show you the, this is your, can you see this? This is your selectively implanted pedestal collectors here, but it is diffused sidewise. So that sidewise thickness also matters in the base collector capacitance. So okay, so intrinsic capacitance, I am not talking about the extrinsic capacitance, the intrinsic capacitance. That is why two sides BSIC will have to be added to WE, and that gives you that. Okay. In silicon germanium advanced nodes, the intrinsic collector doping is much higher than the doping in the extrinsic region of the collector that we talked about, to reduce the Kirk effect and also to ensure the light doping on the side reduces the base collector capacitances. Compound semiconductor, you do not do all this finer tricks, because the device itself can be really high performing, so you do not have to go into such minor details. You can get reasonably good Kirk effect onset and things like that. Okay. Finally, we come to the concept of graded base silicon germanium HBT. There is a lot of mathematics in deriving these expressions which we are going to skip here, but with and without grading germanium in the base, what are the advantages that you get? Okay. So the beta, the current gain beta of a graded silicon germanium base versus just a plain silicon base, the advantage you get is this expression. It is a fairly complicated looking expansion, but you do not have to worry about it. Delta Eg max is the difference in the band gap that you are getting because of grading in the base from the emitter side to the collector side. These are some process parameters. Okay. Typically they have some values here, and then similarly the early voltage ratio with and without the grading also depends on the total band gap difference that you are having from the emitter base side to the base collector side. Always remember that you have more germanium concentration near the base collector, which means the band gap is lower near the base collector junction. Okay. Only then you get a feel like that. So electron that you are injecting from here will kind of swept away this side. Okay, it can be swept away this side, but again there is a notch that will happen if you have a collector silicon suddenly with respect here. So some kind of grading might be necessary at that point also in the depletion here. Now emitter is identical to silicon HBT, so base current is not affected here because the base current is determined by the emitter. However, the base profile affects the collector current, so the graded base profile will only affect the collector current, and we are getting this ratio because of that. There is an early voltage advantage, there is a beta advantage, and then there is a transit time advantage also, because of this extra field that you are introducing. There is a transit time improvement, extra field that you are introducing. That is why you have an improvement in the transit time, and that all of this, and this picture may not, it is actually from an old book, and so it may not be very clear, but I will tell you on the y axis is the improvement factor, how many times by a factor of what are you improving the silicon germanium graded base with respect to a baseline silicon BJT only. On the x axis is the difference in the band gap because of the grading. So at 0 it means there is no grading. At 10 it means the ratio of the difference of the band gap that you have between the n to n of the silicon germanium, that is the total band gap difference that you are having, divided by kT is 10. So it is 10 times kT. So at room temperature that is like 0.26 electron volt, that is reasonably good. So the current gain is this is your current gain, this is the improvement in current gain. So for instance, if you grade it 6 times kT, the band gap difference between the graded the end to end from the emitter base to the base collector, the band gap difference that you have in grading the germanium, silicon germanium, if it is 6 times the kT, then you, for instance, you get a improvement in the current gain as a factor of 2, 3, 4, 5 times, a 5x improvement in beta you get. Okay. This is your early voltage. The early voltage is improved by a factor of 20, 30, 40, 50, maybe 50 or 60, a 50 times improvement in early voltage, that is very, very good. And then this is the base transit time, the base transit times becomes lower, lower, lower until here. So at this point you have a base transit time which is lower than by this is 0.1, so 0.2, 0.3, 0.4, maybe 0.3 times. 0.3 times the original transit time. In a pure silicon BJT, you have a certain transit time, say 1 picosecond. If you do everything, keeping everything same, if you just do the grading in the base, silicon germanium grading because of the quasi electric field, extra electric field, if you have 6 times kT as the total band gap difference, then you have a 0.3 times the transit time, you are going to get 0.3 picosecond. That is a significant improvement in your transit time. Okay. So these are the improvements that you can see with grading the silicon germanium base. Okay. Now with more aggressive technology nodes, silicon germanium HBT also needs scaling. So there is vertical scaling, there is lateral scaling. You have to apply some scaling rules. So when you scale the thickness of the silicon germanium layer, one thing that you have to do is that you have to increase the slope of the grading. So initially you had a thickness of silicon germanium as such, and you had a grading slope like that of germanium increased concentration. But now you have made it narrower, you have scaled it down. So your slope of the germanium grading also has to increase. Okay. Similarly your collector was wide, now your collector is also narrow base, narrow collector. So vertical scaling, when you scale the thicknesses of the epi layers, it helps reduce the transit time because the thicknesses are reducing, and what will happen is that your Kirk effect will get to higher current density. Okay. And it helps you achieve optimal trade off between the cutoff frequency and the breakdown voltage. You have to be very careful when you shrink the device vertically, you need to be careful about the trade off between the cutoff frequency because it will improve, but the breakdown may become worse because you are reducing the vertical dimension, your breakdown may happen sooner. So that trade off is very important. Okay. That trade off is very important. You have to increase the doping, and that also when you scale vertically, and that increase in doping helps the Kirk effect to be pushed to higher value, but it also adversely impacts the breakdown voltage. Okay. So the way the people scale vertically is that you have to thickness by a factor of say S, then you have to increase the doping by a factor of S square, and the germanium concentration as well as the germanium doping has to be increased by a factor of slope S, then you maintain a similar field profile in a way. Okay. So initially you can see that this is the cutoff frequency plotted with respect to the collector current density. Okay. So this dot dashed line was initially, for instance, for a certain technology node you have a cutoff frequency that increases with collector current, and that at the onset of Kirk effect it will start decreasing, that we have discussed in one of the last lectures. However, when you scale it, you will push the Kirk effect to the higher value. So initially you are getting it here, but now you have pushed the Kirk effect to a higher value. So you get higher cutoff frequency because of the vertical scaling, your thicknesses have reduced, your transit time has reduced, your cutoff frequency has improved at a higher, and your Kirk effect threshold has become large. So you are getting the onset at large, which is good, and then it falls down here. Okay. However, breakdown will suffer as I told you. And why do you, that is for vertical scaling. How do you do, why lateral scaling? When you laterally scale the device, which means you have an emitter like that, top view, okay, this is the base, you decrease the spacing between the base and the emitter finger, that is the lateral scaling. Lateral scaling will reduce the base resistance obviously when you bring the base closer to the emitter. It will also reduce your base collector capacitance because you are shrinking them laterally, you are bringing the pads closer. Okay. Ideally it should increase your base collector capacitances, but you can design such that you have the doping profiles and then you have the base collector pads, you tend to shrink them all closer to each other. Okay. And base collector capacitance base resistance, all these things depend on in a way both doping, vertical, lateral scaling, everything, but you cannot just do vertical scaling keeping the lateral scaling different. What I mean is that if you look at a transistor, a field effect transistor, FET or a HEMT, you reduce the gate to channel distance, but you also have to reduce the source to drain distance, otherwise you do not get the advantage. Okay, you need to preserve the cutoff frequency and you need to preserve the the noise figure and the oscillation frequency. And how do you achieve the lateral scaling? You have to scale down not only the spacing between the emitter and the base, the emitter stripe itself, the emitter dimension itself has to be shrunk down. You have to decrease the emitter width by S. Okay, you have to shrink the emitter base spacing by a similar factor. Okay, and then you have to shrink the emitter lateral spacing. If you have 2 fingers of emitter, you have to also shrink them down. So that way you are able to push the lateral scaling also. Okay, so if I look at the record performing silicon germanium HBT, then this is an SEM image of a very state of the art silicon germanium HBT. You can see as a function of collector current density, I believe the record Fmax is about 700 gigahertz for silicon germanium HBT. This is achieved in a, see, this is the area of the emitter. Okay, this is the area of the emitter, and you can see there are 8 fingers actually here. Whether they are connected in parallel I am not sure here, but it seems 8 finger. 1 micron is actually this. This is your 1 micron, and this is your 0.1. This is your 0.1 100 nanometer 0.1 micron width. So in that kind of an HBT, silicon germanium HBT, at a base collector voltage of 0.25 volt, they are able to get 700 gigahertz of Fmax as the peak at a certain current density here. The cutoff frequency FT is around 450 or 500 gigahertz, and after that it rapidly falls off here because of Kirk effect, correct? Okay, so this is pretty much the state of the art, but many commercial silicon germanium HBTs will not be using this particular record figures of merit. They will have probably 300 to 400 gigahertz of FT Fmax values, and they are used for millimeter wave application, for instance. Okay, so this image here shows Fmax versus FT. You want ideally to be at this point, higher FT, higher Fmax. There is this company that has almost achieved that at 700 gigahertz and 500 gigahertz. This is the particular data point here, but bunch of commercial devices are here, 300 to 400 gigahertz and also 400 to 500 gigahertz of Fmax. Okay, over there. These are commercially available, even academic reports are there. For compound semiconductor in gas indium phosphide based HBT, the record is even higher. This is a record, I believe the record from last to last year is 1.2 terahertz of oscillation, maximum oscillation frequency. Cutoff frequency FT is lower, it is probably around 700 gigahertz or something, but the record high FT is also around 750 or less than 800 gigahertz. To the best of my understanding, people have not shown an FT exceeding 1 terahertz so far in any type of transistor in the world. Okay, but I may be wrong, but this is pretty much the state of the art. Fmax 1.2 terahertz is reported, and this is the epitaxial stack. It looks fairly complicated. You see this is an SEM image. They have an emitter fin. What they call as an emitter fin is essentially like a mushroom shaped emitter to increase the emitter to reduce the emitter resistance in a way. Okay, so they have this kind of a mushroom shaped fin shaped emitter profile there, and you can see that this is a very complicated looking stack. They have an indium phosphide substrate, by the way, and the bottom line of this stack is that this is actually you can see that there is an gallium arsenic and arsenide antimonide. Okay, there is a graded gallium arsenide antimonide layer here, and there is indium phosphide emitter. There is a graded antimonide and gallium arsenide antimonide base, then there is indium phosphide collector. Do you know how the band diagram of this will look like? Of course, there is a graded layer, so it will not be identical to what I am going to show, but if you recall many slides back, we had shown that in compound semiconductor you have a very special kind of heterojunction, which is this. Remember, maybe I can remove the annotation here, and you can see this is the gallium arsenide antimonide base here. This is that particular type of heterojunction barrier offset. This is the indium phosphide collector, except in that particular paper with 1.2 terahertz record, they have a graded base here. Okay, they are doing some additional quasi electric field tricks or tailoring there, but this launches the electron. This is the launcher, the launches the electron, and that's very good. It's just, there's no impedance or there's no hindrance to electron being launched from the base to the collector, and this part is highly doped to reduce the top contact resistance. This gives you good breakdown voltage. So they have a record cutoff frequency in compound semiconductor which is 1.2 terahertz, and this was reported very recently. Now coming to practical issues, practical topic, BiCMOS rather than simple silicon germanium HBT, people use a BiCMOS process. What is a BiCMOS process? You use bipolar devices in a CMOS process. You try to take advantage of the best of both worlds. So CMOS process is very large mass scale fabrication is done, low cost, very large mass fabrication, CMOS. Another advantage is that because the CMOS has a MOSFET which is a gate and an oxide, right. So there is no static or very minimal static power dissipation. You do not inject base or the current in the gate. So a very low power dissipation. You can have very high integration with CMOS. Now what are the advantages that bipolar devices bring? Because they are not of very low power static loss, they have high static loss because the base current injects into the base, right. But bipolar devices give you extremely high cutoff frequencies and very high gain. These are useful for RF application, mixed signal, analog, high frequency analog RF application. You can get very high GM and you can get very high FTF max. To get a similar FTF max and GM in CMOS, you need to go down to a much more aggressively scaled node of CMOS. That will increase the cost manifold. So for instance, you have 130 nanometer or 0.133 micron node. In that CMOS node, you have certain performance. In that CMOS node, the HBT, silicon germanium HBT will give you much higher GM and FTF max. To match that GM FTF max, a CMOS might need 90 nanometer node and that cost might increase more. So people combine both these two processes in one flow, like you keep the priority on CMOS, but you also co-implement the bipolar silicon germanium HBT process here. This BiCMOS can give you very high speed, good noise figure, and it's useful for RF receiver application. For instance, automotive anti-collision automotive radars use 77 gigahertz BiCMOS process, many things point-to-point radio transceivers, lot of automotive radars, they are all going towards the BiCMOS process. Not only that, even cellular infrastructure have a lot of BiCMOS proliferation there, okay. It helps you integrate more, get best performance here. So this image here shows you like the schematic of a receiver, for instance. So this RF transceiver with the low noise amplifier, the switch, etc., can be implemented in BiCMOS, and this is implemented in BiCMOS in many applications. Of course, the power amplifier is a power hungry beast, that's a different ballgame. But the RF transceiver, instead of having purely CMOS or RF MOSFET or RF CMOS, it's better to go to BiCMOS. It will give you a cost advantage, it will give you performance advantage. If you need very high end like an antenna switch or a beamforming IC switch, then people may use RF SOI, which is a little bit more expensive, but then again that gives you excellent isolation and very good performance, okay. But BiCMOS is still very promising, very useful, and this particular block is implemented in BiCMOS in many cellular base station architectures, okay. And the digital part, the signal processing, the baseband, everything else is CMOS, the digital CMOS. So it's a combination of CMOS and bipolar process, so it's a BiCMOS process, okay. Just please remember that. And typical BiCMOS processes will have, as I told you, 300 to 400 gigahertz, 500 gigahertz probably of cutoff frequencies, okay. And this is double polysilicon, I already told you that about that. However, there is a challenge when you combine BiCMOS with CMOS, bipolar CMOS, there is a significant problem. There's a challenges that are being overcome, but you have to live with it. So the priority is given to CMOS process typically, which means all the thermal annealing, the thermal budget that you need for CMOS is not altered as much. Now those thermal budgets, the thermal temperature process for CMOS might adversely affect the bipolar process. So this is a compromise that you have to live with, okay. Especially in HBT you have very highly scaled base and the base profile, everything matters so much. When you do this high temperature thermal budget process in CMOS, you may adversely affect the bipolar device, and that becomes more crucial in a more scaled node, okay. At larger node it's still okay, but scale node is very difficult, okay. Also the number of patterning you need to build a silicon germanium HBT can be very challenging. As you can see, the silicon germanium process has much thicker metal because they carry higher current, it's an RF device, whereas the CMOS process being digital logic carries lower current densities, so their metals are also thinner. So the overall metal stack in CMOS is thinner than in the BiCMOS. So this metal stack thickness difference is also an headache, it's a pain, and the patterning steps of CMOS should not adversely impact HBTs too much. It impacts some, but that's not a problem, okay. You have to make sure that it does not kill the BiCMOS completely, okay. The bipolar process will have its own process, right? I mean it will have its some of its unique flavors, and that should not degrade the MOS. CMOS is the primary concern, okay, typically. And these thick metals that you are using, it's all the back end of the line, you know, these thick metals that you use are because your bipolar processors, RF devices are going to carry higher current, so you need to consider electromigration, heating, resistance, etc., none of which matters so much in the CMOS digital logic circuit. So people in digital logic, they prefer thinner metals, of course, because you are scaling down aggressively the CMOS. So when you have thinner metals, then you put a constraint on the current carrying capability for the silicon germanium HBT, because you are using the same processes. Silicon germanium HBTs want to carry high current, but the thinner metals will put a limit on how much current you can carry. So this thickness of the metal vis-a-vis the electromigration capability, the current carrying capability, CMOS preferring thinner metal, bipolar devices preferring thicker metal, this is a big dilemma in the back end of the line, and this dilemma becomes worse when you go to like 45 nanometer, 32 nanometer. It becomes extremely difficult to manage, you know. So this is something that we should generally keep in mind, okay. At 130 nanometer and above, this probably is, you know, taken care of more or less, okay, but this is a challenge that one should generally keep in mind. So the last part is just a quick comparison between FET and BJT before we conclude this this episodes here. What are the main differences? Of course, HBT is a vertical device, FET is a lateral device. Typically in FET, your cutoff frequency will depend on the gate length, which depends on the lithography tool capability. However, in HBT the cutoff frequency will depend on the thickness of the base, and the thickness of the base depends on the epitaxial you know, the layer thickness, and of course the conventional lithography. HBTs can give much higher GM than field effect transistors like HEMTs, MESFETs, MOSFETs, FETs, etc., because in field effect transistor the drain current goes only linearly as the gate voltage or the square of the gate voltage, but in HBT and BJT the output current, the collector current, goes exponentially as the input voltage. That is why your GM can be significantly higher in HBT. In HBT you need much smaller area because you have very high current density. In FET, to increase the current you have to increase the periphery of the device, and you end up spending lot more real estate. In vertical device the field draws vertically, so it's easier to control, there is no surface dangling bonds, moisture, etc. effect, but in transistor like a lateral field effect transistor, your gate drain region, all kinds of moisture, passivation, surface dangling bond defects, etc. can really impact your cutoff frequencies, your breakdown is very sensitive to the surface, okay. HBT is better in uniformity because it only depends on the band gap, mostly depends on band gap, but in field effect transistor your thicknesses are very important. In your HEMT, for instance, your top L-gas barrier or L-GaN barrier is very critical, but in case of HBT the top emitter thickness is not so critical because the band gap is critical. Your diode like behavior, the band gap is more critical than the thickness. In HBT you have a default enhancement mode device because the diode turns on at a particular say 0.7 volt, you know, it's a default enhancement mode device, but many of the compound semiconductor FETs are actually D mode, so you need a negative supply. That's a headache, you know, and it's not very trivial to make an enhancement mode unless you are a silicon MOSFET. HBT process can be very complicated because if you have to etch base mesa, collector mesa, etc., but HEMT, you know, or FET, you know, it's relatively simpler in mass production. It can be a planar process, it's easier to route metals, but HBT, because you have a top, you know, vertical device, you have to make it planar, otherwise routing may be difficult, okay. Again, your HBT can exhibit collapse of current gain, but in an FET you do not have this positive feedback, because in an FET what happens is that when you heat up the current will drop, and when the current drops the heating will reduce, so it's a negative feedback. So that is a good thing in a lateral. So there are pros and cons on both sides of the spectrum. That's what I wanted to say. Now the last question that I'd like to leave you to ponder, you know, just to think for yourself, is why there is no wide band gap such as gallium nitride based HBT commercially. They are not very successful, they are not at all successful. There is no commercial gallium nitride or any other wide band gap based HBT that is out there in the market. This is because of the problem of p-type doping, okay. The p-type doping is horrible in wide band gap material, and the sheet resistance is terrible, the contact resistance is terrible, and so because the p-type is the base is very bad, okay, it makes it extremely bad HBT. Despite this, LEDs are very successful, which also use p-type because they have p-type contact for injection of holes, but in HBT you need the p-type for your recombination. You have a more sensitive active layer in HBT than in an LED, because in an LED the active layer is not the p-type, it's your quantum well. In LED the p-type is only for a contact to inject holes, and hole efficiency of injection efficiency of course matters. That is why in deep UV you do not get, you get terrible LED typically with ultra wide bandgap, but that is a different story. So the bottom line is that in ultra wide bandgap material, HBT is extremely difficult. There is no commercial technology out there yet. Okay. So with that we will end the lecture here today. We have covered bipolar RF devices starting from silicon BJT to silicon germanium HBT, compound semiconductor HBT. We talked about the fabrication on to some extent, and also of course about the parasitic resistances, capacitances, trade-offs, a comparison between BJT bipolar device and field effect transistor and so on. Okay. So that concludes our discussion on bipolar devices. From next week we will have a few lectures on understanding the basics of microwave engineering from device point of view, but most of that is again 101 of microwave engineering. So it would be encouraging if you can just maybe revise through or go through some basic microwave engineering courses, because we will only discuss so much as is needed for understanding devices. Okay. So I will meet you in the next class. Thank you for your time.